which is properties of numbers. So in this topic, what we are going to see is predominantly we'll be talking about factors and multiples. These are the main two concepts, and then at the end we will have something related to the last digit and the cyclicity part as well. So let's start with this. The first part is factors and multiples. So factors and multiples, suppose let's take a number 24, and if we want to factorize, or if you want to write this 24 as product of two numbers, we can write it in many ways. For example, 1 into 24, or let's say 2 into 12, or 3 into 8, or 4 into 6, and so on. So these are all the factors of 24. There are total 8 factors of 24 if you count 4 pairs, 8 factors. Multiples if we talk about, obviously in simple words we call it as 24 के table में जो number आने चाहिए, they are called as the multiples of 24. 24 2s are 48, 3s are 72, 4s are 96, 5s are 120, and so on. So in simple words, multiples can be infinite, because it's like you added 24 in the previous number, you will keep on getting the next number, and so on. And whereas factors is always going to be a limited number, multiples can be infinite. So that gives us one more relation, that number of factors for any number is always less than or equal to the multiples. This is a very quick introduction what factors, what multiples are. Now we will see how to calculate factors of any given number. For that, the first step is very critical, which we call it as prime factorization. So 24 can be prime factorized as 2 raised to 3 into 3 raised to 1. The third step that you all are seeing, prime factors में convert करना है, is what we are looking for basically. Now the part that I'm talking about, calculating the number of factors for any given number. For example, 24 is a very small number, so we could have manually written the factors, the numbers which are going to divide 24 completely. But suppose if the number is very huge, obviously you can't do the manual work. There has to be something like a formula oriented, some sort of thing wherein which you can just substitute the values and get the answer. And that is exactly what we are going to explore right now. The first part is obviously a lengthy method, and then eventually we'll end up getting the shortcut formula part of that. So pay attention. Same number 24, prime factorization we already know, 2 raised to 3 into 3 raised to 1. Now if we just break down all these powers, this is what we have. And if someone asks you what are the 8 factors of 24, so what you are going to do, you are going to multiply each of the powers of 2 with all the powers of 3. For example, you will multiply 2 raised to 0 with both 3 raised to 0 as well as 3 raised to 1. So when you multiply 2 raised to 0 into 3 raised to 0, you get 1. 2 raised to 0 into 3 raised to 1, you get 3, and so on. The cycle will keep on repeating itself. So someone asks you, which are those 8 factors? This is how you can easily figure them out. Multiply each of the numbers from left side with each of the numbers on the right side, and that's how you get the 8 factors. And if you notice the pattern, you will realize on left side you have 4 choices, on the right side you have 2 choices. 4 into 2, you get 8 factors. Now what usually happens is examiners would most of the time will be concerned with how many factors and not which are the factors. So your focus is also to get the answer how many factors. So if you observe, 24 has 2 prime factors, 2 and 3. 2 has a power of 3, 3 has a power of 1, and you see that left side you have 4 choices and right side you have 2 choices. And if you understand that, all they are doing is just add 1 to the power and multiply. So 3 plus 1 you get 4, and 1 plus 1 you get 2. 4 into 2, 8 factors, and that is what the formula is all about. So suppose there is any big number, you want to calculate the number of factors, the first thing is going to be very critical, which is the prime factorization. So suppose you prime factorize the number like this in a generic form, where P1, P2, P3 are the prime factors, A, B, C are the powers of that prime factors. And how do we calculate the number of factors? We just simply add 1 to the powers and multiply everything. So formula becomes a plus 1 into b plus 1 into c plus 1 and so on. So remember this, folks. This is a very important part of this topic. Now let's continue this theory. So there are certain notes. Suppose in a perfect square. So let's consider a perfect square. 400 prime factorization is 2 raised to 4 into 5 raised to 2. 20 का square है ये. And if you observe a pattern, the prime factors of a perfect square will always have a even power. The prime factor of a perfect square will always have a even power, and that is the note that you are going to remember. The first note as far as perfect squares are concerned, and this is applicable to all the perfect square. You can generalize this blindly, don't worry. The second note, obviously, now suppose if somebody asks me 400 के कितने factors है, what I'm going to do, I'm just going to add 1 to the powers and multiply everything. And because we have just now seen that a prime factor of a perfect square always has an even power, so for calculating the number of factors, when we add 1 to it, it becomes odd, and we multiply all the odd numbers, the result is also odd. Basic mathematics, I hope you understand that. And that is what is going to be the second note is all about, that the total number of factors for any perfect square is always going to be odd. So remember this note as well. So these are the two notes which are related to the perfect square. Similarly, there is one more related to perfect cube, which is obviously, let's consider an example of a perfect cube. So suppose 8000, which is 20 ka cube, and the prime factorization is 2 raised to 6 into 5 raised to 3. Now when you observe the powers of a prime factor, you would not able to understand because sum is odd. I mean, one of them is odd, one of them is even. We can't generalize really anything. But if you observe into more detail, what you end up realizing is that for any perfect cube, the power of a prime factor is always going to be a multiple of 3. The power of a prime factor is always going to be a multiple of 3. And that is again applicable to all the perfect cubes out there. So these are the two notes which will help you to simplify any questions related to this particular idea. The next part is writing a number as a product of co-prime factor. Now co-prime factors again is very critical. For example, same number 24. Again, the first step is very important, which is prime factorization. So once you prime factorize the number properly, what they say is, now this power 2 raised to 3, they say that don't separate it out, don't break it down and separate it out like this. One side you write 2 raised to 2, other side you write 2 raised to 1. Because when you do that, now next time when you try to take anything common from all these two brackets, you would realize that 2 will be a common factor as well. And if 2 is also the common factor, then they won't be co-prime to each other. And that is the reason why you're not gonna break this down like this. Otherwise, they won't be co-prime. So what you do ideally is, don't try to break down the power, keep the numbers separate. For example, something like this. 2 raised to 3 on one side, 3 raised to 1 on other side. Now when you try to take common from both the numbers, you would realize except 1, there is nothing really is common. And that means they become co-prime to each other. So this is one way of writing this, and the simplest way that you should not forget ever is 1 into the entire number, because if you remember the note, 1 is always co-prime with all the other numbers. So basically the number is a smaller number, so obviously the number of ways of writing it as a product of co-prime factors is also only 2 ways for 24, and these are those 2 ways. So again, the emphasis is on the prime factorization because that is what it is all about. Okay, now the second idea is basically last digit and cyclicity. Now last digit and cyclicity is very interesting topic. The simple word in a simple word with which we can define cyclicity is the number of powers of any digit after which the last digit repeats. So what we are going to do is we are going to do it for every digit, because we don't know in exam which will be the last digit out of all the 10 digits that we have available with us. So it is very important for us to know the cyclicity of all the digits. I mean, which for which digit the last digit repeats after which power, the last digit repeats after whichever power is called as the cyclicity. So let's start with 2. For 2, 2 raised to 1 is 2, last digit. 2 raised to 2 is 4. 2 raised to 3, 8. 2 raised to 4, 16. That means last digit is 6. And 2 raised to 5 is 32. That means after the fourth power, in the fifth power, 2 raised to 5, 32. The last digit 2 again repeats itself. So after the fourth power, the last digit is repeating. That means 2 has a cyclicity of 4. 2 has a cyclicity of 4. Similarly, we are going to do it for each of the digits. For example, suppose when we take so there, before we go to the other digits, suppose there is a question. Suppose last digit of the question will be like this: last digit of something raised to something. Now, if there would have been any other number before 2 as well, for example, suppose the question would have been what is the last digit of 3, 2, 7, 8, 9, 2, such a huge number, raised to 1, 4, 7, 9. Suppose the question would have been this and not maybe this simple. This is not simple actually, but still. The point is whatever is ahead of 2, it all doesn't matter. It is all irrelevant for you, because again you are going to be only concerned with the last digit. So remember this, don't be scared if examiner tries to fool you with such ideas, such tricks. Don't be afraid. For you it is last digit which matters the most. So for you this question still would have been 2 raised to 1479 ka what is the last digit. The process is pretty simple. What you just simply do is divide the power with the cyclicity of the last digit. Listen to this carefully. Divide the power, which is 1479 in this case, with the cyclicity of last digit. Last digit is 2, and we have just now seen that last digit of cyclicity of 2 is 4. So we are going to divide this power by cyclicity of 2, which is 4. When you do that, you end up getting a remainder. Just tell me what is the remainder if you divide 1479 by 4. When you divide 1479 by 4, you end up getting the remainder as 3. And once you get the remainder as 3, you are just going to find out what is the last digit of 2 raised to 3. So if you remember, last digit of 2 raised to 3 is 8, and that means this number 2 raised to 1479 will also have a last digit of 8. So this is how you figure it out, the last digit for any of the questions that you will tackle after this. Very simple idea. Divide the power by the cyclicity of last digit, and hence you should know cyclicity of all the digits, because you don't know in exam which digit will be the last digit. You just figure out the remainder. Remainder is 3. So 2 raised to 3 ka whichever is the last digit, that becomes your answer. Remember that. Same is going to be the question. The next one, 2 raised to 2684 का क्या है last digit. Same process. 2684 को 2 के cyclicity यानी 4 से divide करो. You realize you get the remainder 0. So 2 raised to 0 यानी 2 raised to 5 का जो भी last digit होगा, 2 raised to 4 का sorry जो भी last digit होगा, in this case it is 2 raised to 4 is 16. 6 is the last digit. So 2 raised to 2684 का भी last digit होगा 16 यानी 6 last digit होगा 6. This is how you figure it out. So remainder 1 आया तो 2 raised to 1 यानी 2 last digit. Remainder 2 आया तो 4. Remainder 3 आया तो 8. Remainder 0 आया तो 6. That's how you do these kinds of questions. So now obviously we have done the quick examples for 2. Obviously we need to figure out for all the other digits. So for 3, let's club something which have the similar cyclicity. So suppose 0, 1, 5, 6 have the last digit has a cyclicity of 1. Why? Because whichever power you take for all these digits, 1 raised to anything is 1, 0 raised to anything is 0, 5 raised to anything, the last digit will always be 5. You can verify that. 5, 25, 125, 625. 6 के लिए भी same process. 6, 36, 216 and so on. So these all digits, the last digit is always going to be the same, so they have a cyclicity of 1. For 4 and 9, the cyclicity is 2 because 4 raised to 1 4, 4 square 16, 4 cube 64. The last digit is repeating after the second power. Same is the case for 9. Then for 2 3 7 8, the last digit cyclicity is 4 because you realize that after the fourth power again the last digit repeats. You just have to take the powers and you will realize that after the fourth power the last digit repeats. This is how you remember all these ideas and you know the process. Then divide the power by cyclicity of the last digit. You figure out the remainder for whichever is the remainder, you just take the power, and whatever is the last digit, that becomes your answer. Then after this, the last part of this is concept of trailing zeros and the highest power. Now how do we get the 0? So obviously we get the 0 by 110. And how do we get a 10? We get a 10 by 1 2 and 1 5. So suppose one sample question, how many zeros are there at the end of 10 factorial? 10 factorial is a pretty huge number. Zeros yani we are looking for 10, so you understand that you have 110 ready made, and 110 you will get from 5 and 2. So because you have two 10s, so in short you are going to have two zeros at the end of 10 factorial. Now when we keep on increasing this, so the simple idea is trailing zeros or zeros at the end, or how many zeros that you can extract, one and the same thing. Zeros you get by 10, 10 you get by 1 2 and 1 5 in simple words. So just to generalize this idea, now what we can do is, as a shortcut method, obviously 2 being a smaller number, you would realize that it will be always present in more numbers. As you can see at the end of 10 factorial, I mean in 10 factorial there are so many 2's out there, but you are not concerned with 2's or 5's individually. You are concerned with a 0, and a 0, for a 0 you need a 10, and 10 is made by 1 2 and 1 5. So 2 being a smaller number will always be more in number, but 5 being a bigger number will always be less in number. So that, you know, shortens our workload, which actually tells us that boss, you should not bother about the number of 2's, but indirectly you should bother about number of 5's, because for 5's you need the equal 2's as well to combine. So 5's जितने भी होंगे उतने 10's बनेंगे, उतने zeros बनेंगे. So indirectly, number of zeros, number of trailing zeros, how many zeros that you can extract, these three types of questions are same as number of 5's that you can extract, the powers of 5's that you can extract, and so on. Pay attention to all these kinds of language where examiner will try to fool you using all these trickeries, but you should not be. So conclusion, number of zeros will depend on 5's and not number of 2's. Now again we can do this in a very, very simple way. 15 factorial, just extract 5 and you realize there are total 3 5's present. So there are total 3 zeros present. Then for 20 factorial, there are 4 5's present and there are 4 zeros present. For 25 factorial, this becomes interesting. People will say 5, but you realize in 25 you are going to have 2 5's. So actually there will be 6 5's present, and that means there will be not 5 zeros, but there will be 6 zeros present. Now suppose there is a huge number, 100 factorial. Now obviously we can't manually figure this out. What we will do is, just forget the factorial sign, just divide the 100 by 5, just divide the number by the power that you are wanting to extract, which is 5, and just figure out the quotient. So if you divide 100 by 5, you get the quotient as 20, and you keep dividing that. So 20 divided by 5 again, you get the quotient as 4. Then you again try to divide, and when you do 4 divided by 5, you will realize it is not divisible anymore. And the moment it is not divisible anymore, that is where you stop. And whatever the quotients that you have got so far, just add them. So 20 plus 4, you get 22. 22 plus 4, you get 28. 28 plus 4, you get 32. 32 plus 4, you get 34. 34 plus 5, you get 36. 36 plus 7, you get 39. 39 plus 1, you get 1. 1 plus 2, you get 2. 2 plus 3, you get 4. 4 plus 5, you get 6. 6 plus 7, you get 8. 8 plus 9, you get 10. 10 plus 11, you get 12. 12 plus 13, you get 14. 14 plus 15, you get 16. 16 plus 17, you get 18. 18 plus 19, you get 20. 20 plus 21, you get 22. 22 plus 23, you get 24. 24 plus 25, you get 26. 26 plus 27, you get 28. 28 plus 29, you get 30. 30 plus 31, you get 32. 32 plus 33, you get 34. 34 plus 35, you get 36. 36 plus 37, you get 38. 38 plus 39, you get 40. 40 plus 41, you get 42. 42 plus 43, you get 44. 44 plus 45, you get 46. 46 plus 47, you get 48 24 fives यानी 24 zeros are present in this particular number 100 factorial. This is the best way, the shortcut way, which is simply divide the number and keep on noting down the quotient and keep on dividing the quotient unless it is not possible, and at the end just add all the quotient. Similarly, suppose even a bigger number, 500 factorial, but now for us it is not scary anymore. Just divide 500 by 5, you get quotient as 100. Divide 100 by 5, you get 20. 20 by 5, you get 4. And when you divide 4 by 5, you realize it is not divisible anymore. The moment it is not divisible anymore, that's where you stop. And once you have stopped, just add all the quotients. So 100 plus 20 plus 4, you get 124 fives are present, yani 124 zeros are present at the end of 500 factorial. Same question can be asked in a different way. As I was saying, what is the highest power of 5 that can divide 500? The same part that we have been doing so far. So keep in mind the number of 5s in the denominator as the number of 5s in the 500 factorial. So highest power of 5, how many 5s you can extract, how many powers of 5 you can extract, how many zeros you can extract, how many zeros at the end are one and the same type of question, and this is how you figure them out. Obviously there will be more sub ideas involved in this, but we'll be doing that all when we do the questions. Digit and everything. So the first part, find the even number of factors for the number 2400. Second question, find the odd number of factors, and so on. So 2400, the first thing, if you remember, for finding out the number of factors, we need to prime factorize that. When we prime factorize 2400, you can write it as 24 into 100 and then further break that down. Eventually you will get 2 raised to 5 into 3 raised to 1 into 5 raised to 2. When you split all the factors as we had done during the concept part, this is what you will end up getting. And now, if you remember, we are supposed to find out not all the factors, but only the even factors. So for even factors, we need the even number. And out of all these numbers, especially even numbers are going to come from the powers of 2. And except 2 raised to 0. Because 2 raised to 0 is 1, which is not even. So except 2 raised to 0, if I consider any power, other power of 2, and if I multiply that with any other factor, I will get always a even number. So right from 2 raised to 1 till 2 raised to 5, there are 5 possibilities that we have. And those 5 possibilities multiplied with any other possibilities of the powers of 3 and 5 will give us the even factors. So 3 raised to 0 and 3 raised to 1, those 2 possibilities, and 5 raised to 0, 5 raised to 1, 5 raised to 2, those 3 possibilities. If you multiply all 3, 5 into 2 into 3, that is 30 as the answer. So 2400 has basically 30 even factors. Second question, odd factors. Now for even factors, if we consider the even numbers, for odd factors, we should not consider that. So 2 raised to 1 till 2 raised to 5 will go off. That means from 2 raised to 5, the possibilities, we will have just one possibility, which is 2 raised to 0. And 3 raised to 0, 3 raised to 1, 2 possibilities. And 5 raised to 0, 5 raised to 1, 5 raised to 2, 3 possibilities. So that gives you the answer as 1 into 2 into 3, which is 6 odd factors. So 2400 basically has 36 total factors, out of which 30 are even factors and 6 are odd factors. This is how you can differentiate. Same question, how many factors are perfect squares and how many factors are perfect cubes? So this is where all the notes that we had studied earlier will come handy. Again, the first step is prime factorization and splitting all the powers. For perfect squares, if you remember the note, the powers has to be multiples of 2. And when you just list down the multiples of 2 powers, from the first set, you get 3 possibilities. 3 raised to 0, sorry, 2 raised to 0, 2 raised to 2, 2 raised to 4. From next one, just one possibility, 3 raised to 0. And from next set also, just two possibilities, 5 raised to 0 and 5 raised to 2. So for perfect square, the powers has to be even powers. That was the note. And when you just compile all of them, 3 into 1 into 2, there are total 6 factors of 2400 that are perfect squares. For perfect cube, if you remember the note, the powers has to be multiples of 3. But here we will add another layer to that, and we will say that include the zeroth power as well. Because the zeroth power of any number is not going to change your answer. So include that as well. And that gives you a refined range now for finding out the perfect cube factors. That is zeroth power along with multiples of 3 power. So from the first set, you get two possibilities, 2 raised to 0 and 2 raised to 3. From second one, just one possibility, 3 raised to 0. And from the next one, another possibility, 5 raised to 0. So 2 is to 1 is to 1. That is total 2 factors that are perfect cubes out of 2400k, 2400k, 36 factors. So answer for that is option 3. Fifth one, how many ways we can write 1260 as a product of coprime numbers? So you'll need to prime factorize that. Once you prime factorize 1260, you will get 2 raised to 2, 3 raised to 2, 5 raised to 1, 7 raised to 1. Now you just need to make the groups that are coprime. Coprime is numbers which have only one common factor between them. And when you just separate out the groups, these are the combinations that you can make it out. Consider one at a time, remaining three at a time. Keep swapping that. Once the 1 and 3 groups are done, make 2 ka groups. 3 such combinations will be there for the alternate pairings. And then last one, most easy combination, 1 into the entire number. Now, obviously, in the exam, you won't be able to doing this much of mehnat. So we will give you a direct formula for this. But for that, the first step is still the same, which is prime factorization. You get the prime factorization wrong, the formula is not going to help you as well. So the formula for finding out in number of ways that you can write a particular number as a product of two coprime factors is 2 raised to n minus 1, where n is the distinct prime factors, where n is the distinct prime factors. So for 1260, there are total 4 distinct prime factors, that is 2, 3, 5, 7. So the value of n becomes 4, 2 raised to 4 minus 1, that is 2 raised to 3. 2 raised to 3 is 8 ways. So this is how you can easily get this done. So most of the time, obviously, the question is how many ways you can write. So you can just use this formula as a 10, 15, 30-second shortcut. But if obviously if you require that in some of the question, you might that which are those ways, then you need to remember the original approach as well. So hence we are telling you both the things according to the situation. You can use one of them. Sixth one, if we have to extract the powers of 21 from 100 factorial, the maximum number of powers that you can get is. So obviously we cannot directly divide by 21 because that's not a prime number. So we'll have to split 21. 21 can be written as 3 into 7. So in short, we have to extract the powers of 3 and 7. But if you had paid attention to the concept part very clearly, you would remember that whenever such is the case, we will always focus on the bigger number, because 3 being the smaller number will always be more in quantity compared to 7 being a bigger number will always be compared to less in quantity. Individually 3 and 7 we don't care because we need them together to form 121. So the number of 21s, the matter of fact is that in terms of learning, that the number of 21s will not depend on number of 3s, but it will depend on the number of 7s, the bigger number. Concept part we did, the number of 10s will not dependent on the number of 2s, because 2 being a smaller number will always be more in quantity.
will depend on 5 because 5 being a bigger number will always be less in quantity. Same idea here as well. So how do we extract number of 7s from 100 factorial? Forget the factorial sign, divide 100 by 7. That was the other shortcut approach. So 100 divided by 7, just note down the quotient, which is 14. Again, divide that 14 by 7, you get 2. Again, try to divide that 2 by 7. If you are getting the quotient 0, that is where you are going to stop. And whatever these answers that you have got, you are going to add all of them. So 14 plus 2, you get 16 as the answer. So there are total 16 sevens that you can extract from 100 factorial, resulting in 16 21s that you can extract from 100 factorial. Seventh one, number of 24s that we can extract from 60 factorial. Now, obviously, 24 again is not the prime number. So 24 needs to be broken down as a prime factorization, which is 2 cube and 3 raised to 1. Now here, obviously, we won't be able to do like in the previous case that we were looking at only at the bigger number. We are only going to do that when the mixing ratio is 1:1. That is, for 121, we need 1 7 and 1 3. For 110, we needed 1 2 and 1 5. But here, such is not the case. For 124 to be made, we need actually 3 2s and 1 3. So the ratio is not 1:1. And if such is the case, that means we need to first find out both of them, that in 60 factorial, how many 2s and how many 3s are there in totality, and then according to the requirement, make the groups and then compare the last part. So let's figure out how many 60s, sorry, how many 2s are there in 60 factorial. So 60 divided by 2, quotient is 30. 30 divided by 2, 15. 15 divided by 2, 7. 7 divided by 2, 3. 3 divided by 2, 1. That's it. Because 1 divided by 2, you will get quotient 0. And that is where we will stop. So add all the numbers, 30 plus 15 plus 7 plus 3 plus 1. That gives you 56 2's are present in 60 factorial. But if you remember, for making a 24, we don't need 1 2, we require 3 2's. So these 56 2's need to be divided in the group of 3, because for 124, we are going to require 3 2's. So 56 divided by 3, maximum you can make 18 groups. Let's see how many 3's are there in 60 factorial. So 60 divided by 3, quotient is 20. 20 divided by 3, it is 6. 6 divided by 3, it is 2. 2 divided by 3, quotient is 0. We will stop there. Whatever the numbers that we have got, we'll add all of them. So 20 plus 6 plus 2, that is 60 factorial has 28 3's present in them. And for making 124, we require just 1 3 and 3 2's. So 56 2's, when we convert them into group of 3's, that means 56 divided by 3, maximum we can make 18 groups. And with those 18 groups, to make the 24, for each of the group, we are going to require 113 every time. That will give us the 24. So even though we have extra 3's, we have in totality 28 3's, we don't need the additional 10 3's, because for them to combine with, we don't have the group of 2's basically. So we will only take the 18 3's with each of the 3 2's ka group to give us 18 24. So mind you, whenever the ratio is 1:1, only then you focus on the higher number and you get away with that very easily. But for such all these examples, you will have to find out both of the numbers that you are supposed to extract, and then according to the condition or the requirement, convert them into specific groupings and everything, and then proceed further basically. So that is the key idea that you need to remember. Eighth one is something that we had done in the question, I mean concept part already. Zeros at the end of 500 factorial. Zeros is tens, tens is 5. So number of 5's at the end of 500 factorial, which is 124. We had already got that. Ninth one, if we subtract 3 from a number, then it becomes a perfect square. Then the original number cannot end in which of the following? The original number का last digit क्या नहीं हो सकता is what we are looking at. So just plot the equation. A number is there. When we subtract 3 from that, the resultant answer turns out to be a perfect square. And if it is a perfect square, then the last digit of that perfect square can be one of the following digits, either 0 or 1 or 4 or 5 or 6 or 9. Now we were wanting to find out the last digit of the number. So the only thing that we'll need to do is shift that 3 on the other side. So it becomes plus 3, and 3 being a single digit will be just simply added to the last digit of the perfect square. So the number will have the last digit has either 3 or 4 or 7 or 8 or 9 or 2. But the question was which of the following cannot be the last digit of the number? And I think from all the options, only 0 satisfies that criteria. Hence, option 5 for that answer. Straightforward question, very easy if you can just realize what kind of data you can plot here and get your answer. Last one, find the last non-zero digit in the following expression. So last non-zero digit. So first we need to confirm whether there are zeros or not. Clearly I can see there are a lot of zeros because zeros will depend on 2 and 5. I can see 25, so that means there are 5s. I can see 2 in either 22 or 24 as well. So first we'll need to break that down. So 25 can be written as 5 square, and that 5 square raised to 13 will give you 5 raised to 26, laws of indices. Then 24 can be written as 3 raised to 12 and 8 raised to 12, but 8 can be written as 2 cube. 2 cube, the whole raised to 12 will be 2 raised to 36. So we have 26 fives and we have 36 twos, out of which 36 twos, 26 twos will go with 26 fives to make 26 zeros. Yani 26 tens basically. So the remaining 2 raised to 10 is as it is. So this is such a huge number that at the end part of this number, there will be 26 zeros. That is the interpretation of 10 raised to 26 at the last part. But if you remember, they were not asking the last digit because it would have been 0. They were asking for the last non-zero digit. This is where the idea of cyclicity and last digit will come into the picture, the concept that we have seen earlier. So 22 raised to 10, for us it is as good as 2 raised to 10. Find out the last digit of that using the concept. So when you do that, last digit of that turns out to be 4. For 23 raised to 11, last digit will be 7. For 3 raised to 12, last digit will be 1. And for 2 raised to 10, again the last digit will be 4 only. When you multiply these numbers, 4 into 4, 16. That is 6. 6 into 7, 42. Then a last digit of that answer has to be 2, which is answer option first. So the first part that you had to remember was to do the simplification, find out how many zeros are there first of all. And when you separate them out, then use the concept of last digit and cyclicity to get the final required answer. With this, we are done with properties of numbers.